Chapter 1: The Impossible Flying Ghost. Imagine a massive, $2 billion military aircraft with a wingspan exceeding 50 meters, roaring through the night sky at high speeds. It weighs tens of thousands of kilograms, burns thousands of liters of jet fuel every hour, and carries enough firepower to alter the course of a war. Yet, on the ultra-sensitive digital screens of modern air defense radar systems, this giant machine does not appear as a terrifying warplane. It appears as a tiny insect, a small bird, or perhaps nothing at all. A surface-to-air missile tracking system. The aircraft simply does not exist. This is not a trick of magic. Nor is it a scene from a science fiction movie. This is the reality of modern stealth technology, the art of making gigantic metal machines vanish in broad daylight from the most sophisticated detection systems ever engineered by humanity for decades. Military supremacy was defined by speed and power. Whichever nation built the fastest jet or the largest bomber dominated the skies. But as radar technology advanced, speed was no longer enough. Long-range radar systems could detect an incoming enemy jet hundreds of kilometers away, guiding anti-aircraft missiles to intercept it before the pilot even knew they were being tracked. The battlefield had become transparent. To survive, aircraft could no longer just outrun the enemy, they had to become invisible. Hi friends, welcome to a new video from Science Simplified. Today, we will explore the extreme physics, geometry, and materials science behind stealth aircraft and uncover how engineers managed to turn giant flying leviathans into phantom shadows. Chapter 2: How radar actually sees the sky. To understand how an aircraft hides from radar, we must first understand how radar actually works. The word radar stands for radio detection and ranging. Its fundamental operation is surprisingly simple, relying on a basic physical principle, the echo of energy. Imagine standing in a vast, empty canyon and shouting as loudly as you can. A few seconds later, your voice bounces off the distant rock walls and returns to your ears as an echo. By measuring the exact time it took for the sound wave to travel out and return, you could easily calculate the exact distance between you and the wall. A radar system operates on the exact same logic, but instead of sound waves, it uses pulses of high-frequency electromagnetic radiation, specifically radio waves or microwaves. A radar transmitter shoots a powerful beam of electromagnetic waves into the sky. These waves travel at the speed of light, 300,000 kilometers per second. If there is nothing in the sky, the waves keep traveling into deep space and never return. However, if those radio waves strike a metal object like a traditional commercial airliner or a standard fighter jet, the metal acts like a massive radio mirror. The electromagnetic energy bounces off the metallic skin of the jet, scattering in all directions. A tiny fraction of that reflected signal travels all the way back to the radar dish on the ground. A powerful receiver picks up this return signal, calculates the time delay, and instantly reveals the aircraft's precise altitude, speed, direction, and distance. For traditional radar systems, a normal fighter jet looks like a massive glowing beacon on the screen. So, how do stealth engineers break this physical echo? Chapter 3: The Geometric Shield. Radar cross-section. In radar physics, the visibility of an object is measured by a metric called radar cross-section, or RCS. RCS measures how large an object appears to a radar system, expressed in square meters. A large commercial airliner has an RCS of roughly 100 square meters. A standard non-stealth fighter jet, like an F-15 or a Su-27, has an RCS of about 5 square meters, roughly the size of a large garage door. A stealth aircraft like the F-35 or the B-2 Spirit, however, has a radar cross-section of less than 0.001 square meters. That is smaller than a bumblebee or a tiny marble. Engineers achieve this dramatic reduction primarily through a concept known as geometric deflection. To understand this, imagine standing in a pitch-black room holding a powerful flashlight. If you shine your flashlight directly at a flat glass mirror facing you, the light bounces straight off the mirror surface and blinds your eyes. This is what happens when a standard aircraft with round, smooth surfaces flies over a radar dish. Its rounded fuselage reflects radar waves in every direction, guaranteeing that some of the signal travels straight back to the radar receiver. Now imagine replacing that flat mirror with a pyramid made of dozens of sharp tilted angles. When you shine your flashlight at the angled pyramid, the light rays don't reflect back into your eyes. Instead, They bounce off at sharp, extreme angles, bouncing toward the ceiling, the floor, or the sidewalls. Because no light rays return to your flashlight, from your perspective, the object remains dark. This is why stealth aircraft look so radically different from traditional planes. Look closely at the B-2 Spirit or the F-117 Nighthawk. They have no round curves on their body. Every panel, edge, and seam is carefully angled at precise mathematical degrees. When incoming radar waves strike the skin of a stealth jet, the flat, angled surfaces deflect 99% of the electromagnetic energy away into empty space, ensuring that almost zero signal returns to the enemy receiver on the ground. Chapter 4, Radar-absorbent material. The electromagnetic sponge deflecting radar waves with clever angles is a powerful defense. But geometry alone is not enough. Sometimes an aircraft must bank, turn, or maneuver, exposing a different side of its body to enemy tracking stations. To handle the remaining radar waves that aren't deflected, engineers created a material straight out of a materials science nightmare: radar-absorbent material, or RAM. If angled geometry acts like a series of mirrors deflecting light, RAM acts like a thick, black velvet blanket absorbing it completely. When electromagnetic radio waves hit a normal metal aircraft, they excite the free electrons in the metal skin, causing a strong electrical current that instantly reflects the wave back out. Radar-absorbent material stops this process by converting electromagnetic energy into thermal heat before it can reflect. RAM coatings are made of advanced chemical polymers infused with microscopic particles of iron ferrite or carbon nanotubes. When a radar wave strikes this special coating, the radio wave penetrates the outer layer and encounters these dense magnetic particles. As the electromagnetic wave tries to pass through the material, it forces the magnetic particles to oscillate rapidly. This friction generates a tiny amount of heat, effectively trapping the radio wave inside the coating and converting its energy into harmless thermal energy instead of bouncing back to the radar. The incoming radio signal is swallowed whole by the aircraft's skin. Chapter 5, Hiding the Ghost's internal engines. Angles and absorbent coatings solve 2/3 of the stealth equation. But a jet plane is not a passive sculpture, it is a roaring, hot machine powered by massive jet engines. And jet engines are a stealth engineer's worst enemy. First, the spinning fan blades at the front of a jet engine are made of bright polished titanium or nickel alloys. To a radar wave, a spinning engine turbine looks like a giant blinding lighthouse mirror spinning at thousands of revolutions per minute. Second, the scorching hot exhaust gases shooting out the back of the engine emit intense infrared heat signatures that thermal tracking missiles can lock onto from miles away. To hide the engines, stealth aircraft use a genius engineering trick called a S-duct or serpentine air intake. Instead of placing the engine directly behind a straight air intake pipe, the intake duct curves in an S shape through the inside of the fuselage. From the outside, a radar wave cannot look straight down the intake pipe to hit the spinning fan blades. The wave hits the curved, ram-coated walls of the S-duct and gets absorbed before it ever reaches the engine. Furthermore, the hot exhaust gas from the engines is flattened out through wide, horizontal nozzles lined with heat-resistant ceramic tiles. These nozzles mix the hot exhaust with cool ambient air before it leaves the plane, drastically cooling down the thermal signature and making the jet practically invisible to heat-seeking anti-aircraft missiles. Chapter 6, The Limits of Stealth and the Rat Race. Despite these mind-bending engineering triumphs, stealth technology does not make an aircraft 100% invisible. Stealth is not a magical cloaking device. It is a delay mechanism. It shrinks the distance at which an enemy radar can track the plane. A traditional fighter might be detected at 200 kilometers away, whereas a stealth jet might only be spotted when it gets within 15 kilometers, by which time it has already fired its payload and turned back home. Moreover, air defense engineers are constantly working on clever ways to break stealth technology. Modern stealth aircraft are optimized primarily against high-frequency tracking radars, the sharp, precise radars used by surface-to-air missiles to lock onto targets. However, older, low-frequency early warning radars operate on much longer wavelengths. When a long radio wave hits a stealth plane whose wing or tail fin happens to match the size of that wavelength, a physical phenomenon called resonance occurs. The entire aircraft structure begins to act like a giant antenna, scattering the long waves and revealing its general position on the radar screen.